Hey, howdy. What's up, y'all? What's crack-a-lagging? um, well, you guys look like a wet dog. I'm just joking. Well, welcome back to Two Men One Course podcast. My name is Pete. I'm your host, Tyler, and I. So we are the co-host of this podcast, and we're happy to see you here. So we hope that you are having an amazing day. All right. So before we get to the details, so always we start with the joke of the day. You guys ready? You guys ready? Okay. Let's go. Um, knock knock. Who's there? It's the bell. It's the bell who? It's the bell not working. That's why I knocked. So okay, not funny, not funny, funny. Yeah, okay, never mind, whatever. So okay, all right. So we hope that I hope that you've learned this before, but if you don't, well, just go over with me. Okay, just very simple. So this. When you learn about this, I think in thermochemistry chapter, right, all the energy and potential energy, something like that. Okay, their heart and soul of that chapter is right here, the law of conservation of energy. So basically, I'll just keep things simple. Heat in equal to heat out, never go anywhere. You can't lose the heat, you can't create the heat. Heat is there, heat and energy is there. They just transform. You can make it, you can destroy it. Okay. So all right, law of conservation energy said heat in equal to heat out. Basically, for example, if you have two objects, one is hot, one is cold, you guys know, so the heat transfer from hot to cold, and at the end, well, how much heat the hot object lose, the cold object gains the same amount, right? We use the opposite side just to show you, or is it losing heat, the other one gain heat. Okay, easy as example. So an ice cube put into a hot tea, all right? So, and you guys should know that the ice gonna melt, right? So the ice absorb heat or energy from the hot tea. And in this case, we can express as, so ice cube gains heat, so positive sign, you know? And tea loses heat, so we use negative sign. That's a law of conservation of energy. So the heat doesn't go anywhere, the energy doesn't go anywhere, they just transfer from one to another or transform. Okay. All right. So something cool. Let's say if I have an equal amount of these two objects. So we have water and an iron. Okay. And then I'm going to heat it up. Let's say the same amount of heat. Let's say 1,000 calories. Okay. Now both objects gonna get hotter. Yeah, you guys know it's gonna get hotter. But who's gonna get hotter more? I mean, well, who's get hotter? Water and iron. Well, in reality, so iron is get really, really hot, but water may be just warm, okay? And this property is called a specific heat capacity. Water can hold heat much more than iron does. Iron can, okay? All right, so specific heat capacity, so it goes like this. So if I have, I'll say, water, and aluminum, iron, and carbon, okay? Same amount, all the same amount. Let's say 1 gram. Keep things simple. It takes about 4.184 joule to heat up this 1 gram of water, and the temperature goes up 1 degree. But it only takes about 0.9 joules for aluminum, 0.4 for iron, and 0.7 for carbon. So water can hold much larger amount of heat, and it resists to change of temperature. Okay, that's what we call specific heat capacity. So 5 to 10 times higher than other elements. Okay, and the specific heat capacity is defined as, so the heat required to heat 1 gram of an object and substance, and the temperature increases by 1 degree. So S equal to Q over M delta T. Delta T is a change of temperature. Okay, rearrange this equation. So heat equal to MS delta T. You probably have seen it before. All right. All right. So one equation, super simple there. Just go with me here. All right. If you want to try, just pause the video first and try to on your own, and then check with me. Okay. All right. Let's say, so if we have 230 grams of metal, and so that's the initial temperature is 25 degrees Celsius, and then put on a hot plate, heat it up. Okay. So that's the heat that goes into the metal, and at the end, the temperature goes up to the final temperature of 30.88 degrees Celsius. Okay, it asks for the specific heat of this metal. All right, so this is how we do. So I know that I'm going to need the change in temperature. So I'm going to go ahead and calculate the delta T. So final minus initial. All right, so you get 5.88 degrees Celsius. All right, so plug one equation, Q equal to ms delta T. Rearrange this equation. So I'm going to get S equal to Q over M delta T. If you don't follow what's going on here, I just divide M delta T on both sides. That's it. Okay. All right, the rest just plug in. So the heat is 1217 joules right there. We got mass of metal, so 230 grams. So plug right there. And the temperature change 5.88 degrees Celsius. Okay. Do the math right there. They just calculator. So right there, ta-da, that number. So 36 36 So 8.899. Round them up, about 0.9 joule per grams per Celsius. Okay, and so the specific heat capacity is a property of the substance. You can compare to the known specific heat capacity value, and it tells you this metal is aluminum, about 0.9, about that. Okay. All right, so a little bit about the specific heat capacity of water. So we talked about water earlier, have the highest specific heat capacity, much higher than other substance, right? And the high heat capacity of water is think about it. If a substance have high heat capacity, so it resists the change in temperature, right? Even the hot day or the cold day, and that's a good thing. Good thing about this though. In our body, we have tons of water, 70-something% of water, right? And everything, all metabolism, enzyme, DNA, anything that how our bodies function rely on the specific temperature of water. Is it too hot, too cold? Our body cannot function. Okay, so it's a good thing that water can resist heat losing or gaining, okay, or temperature change. Okay, so if some other object like is it concrete, so look at 129 degrees, you can fry eggs on it. So right at that high heat, our enzyme, DNA, things not working in our body. Okay, so that's the reason why we have a lot of water in our body. All right, now moving further. So and for an object or substance that you can't really find specific heat capacity, for example, not sure if you have watched Breaking Bad. So this guy got used, so they're making a crystal meth in a large scale, right? Big scale. So they use a reactor. And of course, when you do reaction in there, not only water, right? The reactor also gains heat as well, right? But it's really hard to get to weight 1 gram of this reactor. Well, in this case, we're going to use the heat capacity. Right, so heat capacity defined like this. So take a look at this equation. You just saw earlier. That's just definition of specific heat capacity. Well, I'm going to move mass to the left side, so time mass on both sides. You get that. Okay, and the heat capacity is defined as, so basically just M times S, right? Mass times specific heat capacity. So basically, you can, in this case, we can really find a mass. So we just call them, all right, let's do the whole thing there. So the heat capacity is defined as the energy required to raise the temperature of a substance by 1 degree, the whole thing, regardless of how its mass. Okay, so heat capacity is defined as the amount of heat that to raise a temperature of a substance by 1 degree. That's it. Right, regardless of mass. And so we got two equations, Q equal to ms delta T, you saw earlier, and Q equal to C delta T. This is heat capacity. Okay, all you have to do is just use the right equation at the right time. All right, I'll give you some example. So when filled the water, a reaction vessel in a manufacturing plant has a heat capacity of 28,000 kilojoule per degree Celsius. If 1.41 times 10 to the 8 joules of heat are added, but by how much will the temperature of the vessel change? Okay, so there's a heat capacity of this vessel, reaction vessel. The heat goes in, that's the amount, that's a lot, right? Delta T, temperature change. Okay, all right, Q equal to C delta T, regardless of mass. All right, we don't need to know the mass of it because heat capacity is as a whole. Right, talk about the whole thing. All right, so rearrange the equation. So delta T equal to Q over C. basically, if you don't know what happened here, so I just divide C on both sides. Okay, plug in. So Q is, what's Q? Heat 1.41 times 10 to the 8 joules. C is given 28,000 kilojoule per degree Celsius. Be careful, it's kilo right there, right? So I'm going to convert K kilo to 10 to the third right there. So be careful. Joules cancel with joules. 1 over per degree Celsius. So basically that's degree Celsius at the end. Okay. 3 sig fig, make it 3 sig fig, round them up, you get that number. There we go. That's it. All right, now let's talk about something more related to what you will be doing in the lab. Okay, so right now we talk about the thermochemistry, and the heart and soul of thermochemistry is the law of conservation energy you saw on the first slide. All right, and to determine the amount of energy, that's the end goal. How much energy transfer, how much energy absorb or release, right? That's the whole goal of thermochemistry. Try to get that, determine the amount of energy. But here's the thing though, energy is intangible. You can't touch, you can't see it. Not to mention to measure it. How do you do that, right? If you want to be able to do that, you have to confine a trapped heat into the one area and then measure it somehow. Okay, it's really hard to do. But well, human's smart, man. So we one of the greatest invention in thermochemistry is calorimeter. Right, so we use this a device that we use to measure the amount of energy and heat specifically. Okay, so what does it do? A calorimeter. So we have a different kind. Okay, the kind that you're going to use in the lab is on the right side here. So just 2 styrofoam cups, yeah, on top of each other. That's it. Really simple. All right. But basically, all calorimeters work the same way, where they keep the energy inside, right? Keep the heat inside. Whatever you do reaction in it, or you drop a hot object in it. For example, let's say that's a hot object, or do reaction, and assume that the reaction releases heat. When this reaction releases heat, water will absorb or trap all those heat to itself, and we use the thermometer to tell you the degree of temperature changes. Okay, and when this happens, well, the reaction loses heat, so negative sign, and all the heat here goes to water, right? So water got positive sign there. See that? And that's just a law of conservation of energy. And then so down here, so we can convert that just heat capacity equation, Q equal to ms delta T. You know the mass of water, you know the specific heat capacity of water, of course you do, and the temperature change, that's from the thermometer. You can calculate the heat transfer from the reaction. That's it. Okay, very, very simple there. Anyway, so the calorimeter can be used in 2 ways, and you're going to use that in the lab this week. Okay, so you can use the calorimeter to determine the heat transfer. Yeah, I just showed you earlier. And then the specific heat capacity of an object, I'll show you. All right, I'll start with the heat transfer. Just repeat it. So this is what you're going to do. And actually, you're going to be doing this in the lab. You're going to heat up a metal, let's say aluminum. I think you use different in the lab. You will see in the lab. Depends on what's available. Okay, so let's say I take aluminum. That's the amount of it, 23.5 grams. So heat it up, set up the heating station. And when it heats up, so let's say water goes up to 100 degrees Celsius. At equilibrium, the temperature of the metal, aluminum in this case, will be 100 degrees. Okay? All right, so we're going to transfer the heat in aluminum to the calorimeter. All right? So pour, quickly transfer the aluminum. So make sure you do it lightly, don't let the water splash around. Okay? All right, so once the aluminum goes down, so it goes down to water, so it releases heat, water gains heat, and then the temperature of water goes up, okay, to 26 degrees. Now, you can calculate the energy or the heat transfer by doing this. Take a look. All right, so this is before, this is after, okay? So, well, aluminum is hot at the beginning. Put into water, gets cold, right? Water is cold at the beginning. Once it got aluminum in it, so absorb heat from aluminum, it gets hot. All right, so aluminum lose heat, water gains heat. Okay, all right, so we want to know the heat transfer from aluminum, so we can convert Q of water, so ms delta T. Mass of water is 130 grams. specific heat capacity of water is about 4.184 joule per gram per degree Celsius. And the temperature change, so final minus initial. So final is 26 degrees. The initial is 23 degrees, so that's 3 degrees different. Okay, and then do the math right here, and you're going to get that's the heat transfer. Okay, so the heat transfer is negative, so which means aluminum loses heat 1,631.76 joule. Make it kilojoule. Here we go, and round them up. So 266 here, so 266 there. Round them down. Okay, that's it. That's how you determine the energy transfer from aluminum to the calorimeter. Okay. Now, from here, you can also find the specific heat capacity of aluminum. Let's say you don't know what it is aluminum. You can find the specific heat capacity of it and then compare to the known value of the specific heat capacity later. Okay. All right, we're going to show you right here. So how do you find the specific heat capacity of aluminum? Okay. All right, so we know now that aluminum releases heat, that amount of heat. Okay. So just basic specific heat capacity equation, Q equal to ms delta T, this is all aluminum, all right? And rearrange equation, so S equal to Q over M and delta T, right there. All right, plug in, so Q. Now, notice that I use the unrounded off value, right? Every time when you round off value, so you add uncertainty to your calculation. So I'm not going to use that. Let's have some uncertainty in it. I'm going to use the raw number from the calculator, right? Leave everything in there. Mass of aluminum is 23.5 grams. Delta T, what delta T is? So, delta T, tricky a little. So delta T is final minus initial, right? The final aluminum, initially aluminum is hot, right? And the final is colder. So 26 minus 100, you get a negative number right there. Okay? And do the math right there, you get that number, still in kilojoule. So I'm going to rearrange or adjust this number real quick. So kilo is 10 to the third, right? That's 10 to the third times 10 negative 4, that's 10 to negative first. Okay, and then to just rearrange it, so you should get 0.938, blah 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 blah, and then you round them. How many sig fig? 1, 2, 3, 1, 2, 3, 3 sig fig. So 3 sig fig, round them down. Here we go. That's aluminum, about 0.9. Okay. All right. So that's how we use the calorimeter. All right. So you can use it to determine a heat capacity just using the law of conservation of energy. You can determine the heat transfer by using the specific heat capacity equation of water, and the specific heat capacity of the metal or aluminum. In this case, you can do that from the specific heat capacity of aluminum equation. Okay. All right. So one practice together with me. All right. So pause the video, do by yourself, and check with me. We get 50 grams of the metal, heat it up to, let's say, that's the starting initial temperature of this object. Okay. Now we throw this object to the in the calorimeter, close it, and then read the heat transfer, read the thermometer. Well, the question asks for the specific heat capacity of the material of this object. All right. So that object loses heat and water gains heat. So there's a law of conservation of energy. Okay. All right. So both of them. So use the ms delta T on both sides. We want to find the specific heat capacity of this metal. More everything we don't want, we know to the other side. Get that? Okay. All right, so we know mass of object, mass of water, specific heat capacity of water. You can look it up. Now, delta T though. So here's what happened. Start with water. Well, water used to be cold and get hotter. So 51.2 minus 24.8. Get that number. But the metal though, so the metal start hot, and at the end it's colder, 51.2. Okay, so 51.2 minus 100, get a negative number. All right, now just plug in. So start from the top first. So mass of water is 50 grams. Specific heat capacity of water 4.184, and leave the unit there. You should be able to see the unit cancellation at the end. Okay, delta T of water. So right here 26.4 degrees Celsius. At the bottom, so we have negative mass of metal. That number 50 grams, same amount. Temperature change, so negative 48.8. Yeah, negative there. So negative and negative become positive. That Yeah, if you if you make 100 subtract by 51.2, you would get a positive number here, and then you're gonna get negative number here, and the specific heat capacity can be a negative. That doesn't make sense. Okay. All right. So unit cancel out, and do the math there. You should get that number 366. All right. That's all the calculation. Okay. Let's check out on the next video. Talk about what you need to do in the lab.